Mr. Rohit Prajapati, who is a Managing Director of Digitoid Technologies, Bangalore. Yeah. Sir is a Managing Director of Digitoid Technologies and he holds 11 plus years of experience in embedded industries. In 2018, Rohit founded Digitoad Technologies with a vision to emerge Digitoad as an advanced center for skill development and product innovation in India. Today, with leading today with leading OEMs such as NI, STM Electronics, Digilent, TMYTEK, Digitoid is working, and as an educational consultant, Rohit collaborates with universities to bridge learning gaps, delivering impactful upskilling programs in IoT, AI, and wireless technologies. So we welcome Rohit sir. It will be a very interesting session because we have already have some collaboration previously to in some other workshop. So it will be very insightful. So please attend it fully, and you can ask the question in the end. Thank you.
Thank you,
Sir, you
Chirag
may
sir.
start.
Yes, thank you, Chirag sir, and thank you for this opportunity to be a part of this Atal FDP program. It's been a pleasure for me. Today, I am also assisted by one of my colleagues, Mr. Chiranjeevi. So he has set up the demo and he will be giving you an overview about how AI for electrical use cases can be implemented. So today's session that I will be handling is titled as Edge AI for electrical use cases. So without further delay, let me just share my screen and start with the presentation. Please let me know if my entire screen is visible.
Yes.
So is this slide
Yes,
visible?
sir. It's visible. Yeah.
Yeah. So is it changing? Can you see the changes, sir? Second slide, third slide.
Yes.
Yes, sir. It is working fine.
Okay, okay. So welcome once again to this session on Edge AI for electrical use cases. Uh, I would I was interested in introducing Digitoad also, but since we have already spent around 20 minutes configuring the things, so I would not take that slide. But just to give an overview, Digitoad is a core technology based company, and we work primarily with academics, industry, and research institutes for research solutions, teaching solutions on different platforms. So we have a very strong knowledge base in the domain of embedded systems, sensor-based data acquisition, test and measurements, AI applications, and recently we have collaborated for quantum computing also. So overall, we focus on emerging technologies, and AIoT is also one of the domain that we have been working over the past 5 years. For AI applications, we have collaborated with ST Microelectronics. Most of you might know about ST because it's a big name in the industry. And with ST, we are working very closely on delivering this education program, or let's say upskilling program for the students to combine the world of AI with IoTs. Okay. So mostly this session will focus on sensor-based application scenarios. AI is a very big domain. It focuses on different. Today we talk about chat GPTs and all when it comes to AI use cases, right? But the domain that we are discussing today totally focuses on sensor-based applications for electrical use cases. Okay. Now, why Edge AI for electrical engineers? So this is one question that we should ask ourselves, right? Now, traditionally, non-computing branches of engineering, right? Let's say anything that is that does not fall under the umbrella of maybe computer science or information science. So let's say electrical, electronics, mechanical, civil, right? So traditionally, this domain of engineering, uh, we a few years back we could not imagine that okay, we will be using AI when it comes to mechanical engineering or civil engineering or electrical engineering, right? But today the entire scenario has changed. Now it's more about multidisciplinary approach for AI applications. The reason, because AI does not limit itself to a specific domain, or it does not constrain itself to specific applications. The applications has widened, and not only this, right? Uh, when it comes to the core engineering modules such as electrical, electronics, we talk about different types of data that we can gather from such systems, such as sensor-based data, right? So more and more electrical engineer has evolved into a sensor-based system, which is largely driven by different data, right? Primarily currents, voltage, temperature-based systems. Now, when it comes to data, and if we have to analyze any system which is driven by data, right? So the only today we can only think about machine learning and AI, right? So this is what has evolved over the past few years with the development in more efficient machine learning models and different ways of solving traditional engineering problems with the help of machine learning and AI. We can only imagine electrical systems to be powered by AI and machine learning. We also know that we'll use a lot of signal processing concepts in when it comes to electrical systems. Without signal processing, we cannot analyze electrical systems. So this is where Edge AI has come into picture. Now, what does Edge AI enables us to do? It allows us to do intelligent decision making inside electrical systems. We will see how it does. Then, because of Edge AI, all this decision making happens within a specific bandwidth and reduced latencies. And not only this, this also allows us to do real-time condition monitoring. So there is just a small image I have put there for some visualization. So let's say we have an electrical pump and we want to find out whether it's working properly or not. So depending on different types of sensor data, we can analyze this system. And all this with the help of a microcontroller. All the models or maybe all the algorithms can be deployed on a small microchip, and it can be used to do all the necessary machine learning execution. Now, what is Edge AI? So here I have presented two different approaches. One is cloud-based AI approach. The other is Edge AI approach. Both the diagrams look very similar when you see from the top view, but if you dig a little bit, you will come to know that both have very significant differentiations, and they are very different when it comes to the efficiency of the overall system. So if we talk about the first one, the cloud AI approach, so let's say we have certain IoT nodes or maybe sensor-based systems where real-time sensor data is acquired. And this sensor data is continuously streamed to a cloud-based platform or maybe some remote servers also. Okay. Now the user can only access this device not directly by communicating with the IoT nodes, but via this cloud infrastructure. So here in cloud-based AI approach, we deploy the AI and machine learning algorithms on the cloud infrastructure. So decision making basically happens on the cloud, right? And for this, you need to continuously stream sensor data, right? But with this approach, there are different challenges because if you have to continuously stream sensor data, you need a system which needs good amount of power, right? Power consumption will be high. When you stream sensor data, there will be bandwidth issues, latency issues, there will be data security issues, right? So all these challenges are inherent to the cloud-based AI approach, right? Now, the possible solution for this is to bring the decision making from the cloud to the device itself. So this is where we see in the edge AI approach, instead of doing decision making on the cloud, we have just migrated it to the device. So what could be the possible solution here? Now, do we have powerful nodes to run the machine learning models today? Yes, we do have, right? We don't need it to be too much power hungry, But at the same time, today's uh, devices or chips, edge AI devices are powerful enough to run all these machine learning algorithms and models right on at the point where data is collected, right? So all the decision making happens here. You don't have to stream the sensor data. Rather, whenever the decision making happens, you send the notification data to the cloud so that the user can access. So with this small change of migration of machine learning model execution from cloud to the device, we make huge progress. In what ways? So you don't need to continuously stream. So you save a lot of power here. Okay. Battery lifetime can be significantly increased. Other thing is we limit the data security issues because we have limited the amount of communication with the cloud. And latency issue is also not there because all the real-time decision making happens right at the point where data is collected, right? So edge AI approach typically solves most of the cloud AI approach, most of the challenges from the cloud AI part. Now, there are different applications where cloud AI has to be done typically, okay? Because if you think about larger infrastructure and if you think about somewhere where you need a lot of processing power, then obviously cloud is the suitable thing. But most of the applications, largely we talk about today, right? For electrical applications and all, edge AI is the best possible way to go ahead. Excuse me. Now, whenever you take up this problem statement, okay, so for example, tomorrow you have decided that, okay, I have my electrical system. Now I want to design a prototype for this, an edge AI prototype for this, right? So you should know about certain workflows. Now, this is a typical workflow for edge AI approach. So if you, we have 5 steps involved. The first one is sensor data acquisition. So whenever you want to have an efficient edge AI product or prototype, ensure that your sensor data is accurately acquired. Okay, because good most of the times your the accuracy of your machine learning model or decision making capabilities depend on the data. So step number one is very important. Whether you are using current, voltage, vibration, temperature, these are the typically common sensing elements that we make use of when devising an electrical use case. So ensure that you have identified like what should be the resolution of the sensor. Are you using a digital or you are using an ADC converter? What resolution, right? What signal strength or maybe what signal bandwidth you are going to sample, the sampling rate, everything should be proper and well defined initially. Then only you can ensure that whatever data you are collecting, those data set is good enough for further process by the machine learning model. Step number two is pre-processing, which means that if you want to remove noise, filtering, if you want to do FFT analysis, right, feature extraction from your raw sensor data, you can do it. Most of the times it's not required, but largely like if you want to further refine your sensor data, right, you can even give raw sensor data to the machine learning model during the training phase and deployment phase also. But if in case if you want to further refine and maybe look at the potential accuracy of the models, right, or performance of the model, then you can do this step as well. So this is optional. Largely, we have seen that we don't use this one. If you are doing some audio-based application, then filtering we do FIR and IR filterings, but largely it's not required. Third step is model training. Now, most of the times, your edge AI device is not powerful to train the model. So we do training offline, which means that you train your model on a PC or on a cloud-based ecosystem, right? So once you have the trained model, you can go for deployment. So today we are working a lot on STM32 microcontroller because that is very suitable ARM Cortex microcontroller to run real-time ML algorithms. So this is the phase where you deploy the model and then inference at the edge. So inference at the edge is the stage where you can do anomaly detection, classification, regression based approaches on the device itself, right? Now, most of the times you have these models, trained models, but there are use cases where if you are doing anomaly detection technique, you can train your model on the device itself. Okay. So this 5 steps are very important when it comes to developing a prototype for your edge AI for electrical use cases. Okay, next page. Let's just get an overview of few of the use cases, largely for electrical systems. Now, use case one, we selected as motor condition monitoring. This has been implemented as one of the use cases. If you go to ST website, you will find a very beautiful article on this, and this image has been taken from the same system. So normally what happens, largely like electrical systems are defined by different types of motors, right? And the signals of interest in such cases are vibration. So you may use an accelerometer or maybe a 6-axis motion sensor. Largely, it's 3D accelerometers that we use. You can have current signature. You might also want to use acoustic or audio signals to capture the audio of the from the vibrating system of the motor. Now, normally, what type of AI tasks do you want to do? So you might want to find whether the motor is faulty. So what is the normal behavior of the motor and how a motor behaves when it's faulty? Or you might want to find the bearing fault detection, right? Sometimes you might also want to find anomalies in the load, right? So that is load anomaly detection. So these are typical three different types of maybe solutions that you might want from your AI system. Now, why AI here? Again, because largely with different sensor data, we can formulate a specific a model to understand how the motor behaves or how the motor performs or how the motor is operating, right? Now, traditionally, what happens before, let's say, maybe few years back, when people didn't think about AI approach for such systems, uh, they did everything manually. So traditionally, they used to do thresholding systems, right? Or if-else loops. So they used to set different FFT thresholds and check under different load conditions. Now, such cases are limited because uh, I mean, you will have just have a limited scope of setting the thresholds. You cannot do it for different, maybe for infinite number of thresholding points. Uh, but when it comes to AI approach, instead of putting on, sorry, instead of keeping thresholds, your approach is basically to train the model to understand the patterns, right? So basically, you want your AI model to understand the patterns hidden in the data, not on fixed values. So AI always dominates in such cases. Okay. So it's always easy for you to generalize your uh, approach to find the patterns hidden in the sensor data. Okay. So use case two is about predictive maintenance. This is again one very important concept when it comes to edge AI. Predictive maintenance is all about reducing the downtime of a machine, right? So let's say if you have boilers, if you have bigger machines, right? In industrial setups, such as industrial drives, conveyor belts, and all those things, compressors, fans, right? So normally, you would like to have a very good idea about how all these machines are operating, at what conditions, and whether they are tolerant to the faults or not, right? So with the help of Edge AI, we can devise out anomaly detection models, which can be further expanded or extended into predictive maintenance-based applications for early fault detections. Now here, you can not only find, let's say, the fault in runtime, but also predict it. Okay. So you can also predict like if a machine is operating at such operating conditions for a specific duration, by what time it will be facing certain issues, or maybe by what time the issues might start appearing, right? So this also leads to one condition known as remaining useful life. Okay. Now, all these concepts and topics are very important when it comes to uh, factory floor maintenance or maybe predictive maintenance based approaches. Okay, it's going back again and again. Third use case, and these are all like very popular ones and implemented by ST in their website. You can find again these use cases: energy and smart grid applications. Now, we all know that the role of smart grid in delivering power to our homes, industries, right? And uh, and how important it is for us to understand the status of smart grids, right? And also understand how efficiently the smart grids deliver power to the users. Now, for this also, we can implement different types of examples such as load classification, energy anomaly detections, right? At the smart grid level itself. Now, there are different data that you might want to collect, maybe the rate of production, the rate of consumption, right? All those things needs to be considered while you have to understand while you have to design a specific example from this use case, from this smart grid application use case. Okay, I'm having maybe it's because of my throat. I'm having a throat infection, so I'm just my voice is not very clear. Maybe because of that. Okay, I have a couple of slides. After that, Chiranjeevi will take over. Okay, just give me 5 more minutes. I will finish my slide. Now, Edge AI comes with its own challenges, right? We have seen like what is Edge AI, why it is important for electrical use cases, and what are the important categories of use cases for Edge AI. Now, it comes with its own challenges. If we just simplify, there are two types: technical challenges and engineering challenges. Now, when it comes to technical challenges, most of the edge AI systems are deployed on microcontroller based systems. Even at our office, or maybe whenever we are doing some prototyping applications, we use ARM Cortex M4 based microcontroller systems because these are low cost systems and these are widely available. But this system comes with its own limitations, right? As you know, most of the microcontrollers, though even though they belong to ARM Cortex categories, they are limited in RAM with few kilobytes of RAM and maybe few megabytes of flash memory. So you cannot deploy a very large algorithm which might consume a lot of RAM, right? Or memory, or maybe it might consume too much of your storage. So that is one challenge. So you always need to have that trade-off. So you need to understand like how big your algorithm can be when you want to deploy that on a STM32 or any ARM Cortex based microcontroller. Low compute power. The CPU itself for a traditional ARM Cortex, you can see a CPU starts from somewhere 40 megahertz and goes up to 180 megahertz, right? So uh, this means that you cannot load lot of parallelly running machine learning algorithms on a microcontroller. So maybe you have to execute it one by one. So computation of a microcontroller is low. So maybe that is also to be considered when you want to design an AGI application. Real-time constraints. Sometimes what happens because of its compute and memory limitations, you might not get that real time uh, uh, real time scenarios which might be necessary for your specific applications. And power consumption. So most of the times these devices needs continuous power. Okay, you most of these devices, the microcontrollers, are powered by batteries, and you might not have the flexibility of using the traditional power systems with this. So you need to understand that, okay, when you are designing a microcontroller based edge AI system, you need to understand that the execution of your algorithms does not consume too much power so that the battery drains out rapidly. Okay, so all those things needs to be considered. But again, with these considerations also, today microcontrollers have become the number one choice for edge AI systems design. The other engineering challenges, as I said during the workflow slide, that data quality. So your machine learning models is as good as your data, right? So most of the times, what challenge we see is that when you use your sensor in your lab, right, it gives you one type of data, but when you go for a field deployment, it gives you different type of data. So that should not happen. The accuracy of sensor, the quality of data coming from the sensor, or the one which you are creating as a data set, right? It matters a lot. You need to spend a lot of time. See, machine learning model does not take much time to be developed and optimized. Most of the time that goes into the life development life cycle is the data quality, working on the data quality. So that is one big challenge. Sensor placement. Most of the times placing the sensor on right position or maybe right part of the machine from where you are collecting the data, right, is very important, because slight difference in the orientation might give you a different. So let's say when you collected the data, right, before training your model, your sensor orientation is one way. If you're using a 3-axis accelerometer, and later on when you are deploying it in the field, it's in a different way. So entire concept or entire output from the algorithm straight away changes, and this we have witnessed a lot of time. Sampling rate selection is one again key factor, because different sampling rates will give you different windowing techniques of the data collection, right? And again, that will again affect your system. So the rate at which data is collected for training your model, and after deployment, the same sampling rate should also be used for inference purpose. Okay, so all these things has to be considered while you design your edge AI systems. Now I would like to give you a quick overview about different tools that you might want to use for your edge AI system. Anyways, Chiranjeevi will give you a live demo on that. So the first tool is Nano Edge AI Studio, which is from ST Microelectronics. So Nano AI Studio is for people who do not have a lot of background in machine learning model development. They are domain expert, but they are not machine learning experts. So here you can quickly make use of different pre-built models. Okay. And you don't require any Python coding, machine learning coding. You just need to get your sensor data, or if you have data set, you can give your data set, train your model for different applications such as anomaly detection, classification, sensor-based electrical signals, right? And NanoEdge AI Studio is very friendly with with data which works for electrical systems such as vibration, current, and audio. Okay, so you can go ahead and give a try to NanoEdge AI Studio. It's freely downloadable from ST website. Possibly we will share a link after the workshop also. The other tool is STM32Cube.ai. Now this is for people who are more into machine learning, right? If you want to develop a model from scratch using Python, such as if you might want to use frameworks like Keras, TensorFlow, PyTorch, scikit-learn, right? And you want your own model to be deployed on the STM32 hardware. So you can make use of Cube.ai, which gives you optimized C libraries, two libraries, model and runtime. And these libraries can be a part of your project build process, and you can deploy these libraries on your hardware also. Now, this is for people who are into advanced stages of machine learning applications. They understand what algorithms are. Largely, Cube.ai we have used a lot for neural network based deployments and image applications. Okay. So these two tools are very essential when it comes to developing and deploying an end-to-end machine learning application on an STM32 hardware, an edge AI application. Okay. So that was all from my end. I think I will, yeah, let me just hand over the control to Chiranjeevi. Chiranjeevi, over to you. Please
Yes, Rohit.
go ahead and start with the demo part.
Yeah,
Then
thank
we'll
you so
take the
much.
questions. Yeah,
Thank you. My voice is clear, Rohit?
yeah,
Yes,
it's
yes.
clear.
Okay.
Yes, yes, it's
Please
audible.
give me a moment. I will share my screen.
Sure.
Can anyone confirm my screen got shared?
Yes, yes, it is
Yes,
shared.
yes.
Okay, thank you so much. So till now, you people got the complete idea how the edge AI concepts will work. Now we are moving ahead with the live demo. So where we are checking with the how practically this edge AI we can able to implement on our microcontroller board. So the main objective why I am showing one project which is overload detection. I am doing this project overload detection with the help of the current sensor and with the help of the L4 series board. So one more thing, like whenever we are working with this overload detection project, the main objective is as follows. So whenever the motor, let's take in our scenarios, especially for the electrical department, we have a lot many motors. We have electrical machines lab, right? So in the electrical machines lab, we have DC machines and we have AC motors and DC motors, right? So generally, we work with the mechanical load with respect to the DC motors. So here also, I just set up one small DC motor with the 5 volts DC motor. So in that, I'm trying to detect the motor overload in the real time, and also with the help of STM32 IoT node, where it can runs the anomaly detection model, where we can able to see how the model will works, and it can spot the unusual patterns in the current data. We can collect the two data. One is the normal data and the one is the abnormal data. And with the help of the normal data, we can try to check what are the unusual patterns in the current data with the lower current when the motor is in normal running condition, and if the motor is running in higher speed, means if the load is more, then obviously the current values are increasing, right? So we are considering that current increased current values as an abnormal values. So that's what our objective here, what exactly we are trying to do. We are trying to implement the edge AI on to detect the motor overload with respect to the current. So we are using the anomaly detection model. Okay. Yeah. So for this, I'm using this this AIoT node STM32 from the ST Microelectronics. So this is the board which has the capability for the sensing, and it has an inbuilt Wi-Fi module. It has an inbuilt Bluetooth and also the NFC tag, and inbuilt sensors are also available. If you see here, it is comes under the L4 series, which is the ultra low power applications we can able to implement. And as Rohit is telling, we are using this ARM Cortex based M4 series. So here in this microcontroller board also, we have the ARM Cortex based M4 series. We are working with those. If you're seeing, it has an inbuilt gyro, axle, magnetometer, humidity and temperature, time of flight, and the audio sensors, and it has an Arduino compatible headers as well. Okay, so here is my demo setup. I will just show to you here in the live as well. Here is my DC motor. Here is my current sensor, and here is my main microcontroller board. I just set up like that. Here I have given connection from my board to this current sensor, and with respect to the IP plus and IP minus, I am seriously connected this DC motor to measure the current. Actually, why we opted for this sensor, which is ACS723, is so it has the capability to detect the lower currents as well. So that is a reason, and it will goes around from 10 milliamps to the 5 amps. Obviously, if you are, we know that in our missions lab we have the current rating around from 9 till 19 amps. Yes, of course, we can able to connect that 230 volts direct power supply to this IP plus positive, and we can directly seriously we can connect the ammeter, we can check, and the current will goes here, and we can check what is the current values with respect to the sensor if we are using this sensor. Yeah, this is the main the demo workflow. The data preparation, these things are already you people got little bit of glimpse. The main the path, the workflow where the data preparation is must and should. We need to collect proper data set. If we are collecting the proper data set, then half of our job is done. Then we need to send our data set for the ML model development in the second stage. So here we are doing in the second stage that one. And after sending our ML model to for the training, after building our ML model, we will get some libraries. We will make use of that libraries for our final deployment in this model implementation. And here also the same thing in the data logger, we are acquiring the ACS 723. We are using the current sensor. And here, with the help of whatever the data we collected from that current sensor, we are taking the data and we are, with the help of that data set, we are building the ML model by using Nano Edge AI Studio from the STM Microelectronics. And whatever the libraries I'm getting from this, I'm deploying those libraries for my final ML deployment, where I can check the inference space. On-device learning, machine learning, I can able to check and I can able to check whether my model is properly working and I can able to get the predicted values or not. Yeah. So I will directly go to the software now. I'm using STM32 software here. So why I am using this software is just for the coding and for the debugging. Here I am using this STM32 BL4 series boards or whatever from the ST microelectronics boards. So this tool, which is from the ST microelectronics only, STM32 Cube ID, is very useful for the coding and debugging. It is like it has some very high features. Let's take if I want to show to you. So here there is one project I have created. After creating a project, there are thousands of boards are there under HT. So it will gives the capability to program that board, and we can able to debug that board. Means whatever the coding we are writing, we can able to code it. So this will works, and it is very useful. Here I have selected my industry this BL4 series board, AIoT board. In this board, as I told, industrial IoT node. So this is the main microcontroller. So this is the internal replica. This is just like a pinout where I can able to configure one particular peripheral into lot many ways. Let's take if I just click on that one peripheral, this is completely interconnected with respect to our board. So I can modify or I can configure one particular pin as per my wish, as per my particular requirement to my project. So this is very, very useful whenever we are trying to do more project and higher end projects like that. So as of now, I'm using the current sensor. So that current sensor will works with the ADC. So it is taking the values from the environment, which is the ADC values. So again, I'm using some coding logic. So with the help of that code logic, whatever the ADC values I'm getting, I'm trying to convert those values with the formulas, and I'm trying to get the current values. And also here, I use it the UART because I want to check the data in the console. So one more use case for this CubeID is useful for this CubeID is whatever the configurations here we are giving in this input output configuration file, the code will get generated by this CubeID only. If you click on this single button where the code generation, so it will just show to you, do you want to generate the code? Yes. And it will generate the complete code, whatever the things we configured in the IOC configuration file. Okay, so this is the main.c file. So what I have done in this main.c file is I have written my user logics. Let's take, I have written the driver files for my current sensor, which is ACS 723 .h file and ACS 723.c file. All the definitions I have written here and all the uh, declarations, and here all the definitions I have written here. And if you go to the main.c file, I just called here, and what is our first step? Our first step is creating the data logger, right? So if I directly tell to my microcontroller board, collect the data set means it can't able to collect. So what I am trying to do with this code, with this current experiment is I'm giving some reference. So I will dump this reference to my microcontroller board. So whenever I'm flashing this code logic to my microcontroller board, it will act like a reference. With the help of that reference, it will collect the data set. So how I have written the logic, I'm collecting or I'm creating a buffer with 256 samples. I'm using only the current sensor with one axis. So I have written the logic here, how the data want to come and how the current samples wants to get stored in the loop or in that buffer with the help of the for loop. And finally, I'm going inside the buffer and I'm printing one sample by one sample at a time at lost. And again, I'm coming to the new line and again, I'm printing the complete buffer and again, I'm printing the complete buffer. That is the reason I have written that logic. I call that function under the while loop. Okay. So these are the few things where I have calibrated my sensor. Uh, it will works with the, I have just connected with the 5 volts here and I have given the 12-bit resolution. As I told, it is working with the ADC. Now I will flash this code logic to my microcontroller board. I will just run this, just connect this. Just now I have connected with the USB cable. I will just run this. Okay. My code completely flashed into my microcontroller board. Okay. Yes. So as of now, I'm seeing here 0 completely. Why it is happening is it is in no load condition currently. Okay. Now, if you check here, I just placed one slider here. I will just turn. If you're seeing now, my current values are increasing. You people know the rating of the current for the DC motor, right? So it is giving me in the milliamps. Okay, 300 milliamps means 0.335 amps like that or 0.4 amps like that. So we are getting in the milliamps. So this is the reference. I will just turn off again. Okay, so this is the reference I just want to give to my microcontroller board. According to this reference, I want to collect the data set in my next stage. Okay, so this is clear. So in the first stage here, I have given the data logger code. In this data logger code, I given the reference. Now I will go to the Nano Edge AI Studio. So this is a software where Rohit is telling to you that we can create an ML models. Even though let's take we are from the electrical department or the mechanical department or these the core branches. The people doesn't have the complete knowledge how to develop a machine learning or how to write the Python language coding completely with compared to the computer science people or like that, right? So, but this tool we have one nickname for this tool. We use it to call it as an like a automated machine learning tool. Even though the people who doesn't have the complete knowledge how to build a machine learning model, how to get the libraries, how to deploy it in the further, that one we'll see further, but how to build a machine learning model. So for those people, this is the one-stop solution. This Nano AI Studio, we will make use of this Nano AI Studio. We can build our ML model. Here, the thing is, we only want to give, or it will only expect the data set, the proper correct data sets from the user. That's it. If you are done with it, then definitely it will only create the ML model for us. You will see that. So I will just give a quick overview again here. What is this Nano AI Studio? How many kind of projects we can able to do? If you're seeing, so this is the UI for this Nano AI Studio. I will just click on the new project here. If I click on the new project, yes, we can able to do 4 kind of projects. One is the detecting the anomalies. Anomaly detection we can able to do, and one is classifying and classification projects we can able to do. And one more is detecting the outliners in your signal. Means it is just like an one class classification kind of things we can able to do with this project. And here the extrapolation. Extrapolation means to predict the future outcomes. This is if you are working with this extrapolation, you want to give the higher data sets. Lot the amount of data sets should be more, so then we can expect the proper outcome at the end. Of course, machine learning means we need to give the data set more. If you are giving the more data set, then only we can expect the outcome better. It wants to predict the outcome properly, right? So that's what. Yeah, here few more are there. A few things like data logger, data manipulation, finder, and feature importance. So the data logger, if you have your board directly, you want to just select the particular board and you want to give the parameters and you want to generate the data logger. Just now we have done in our previous step in the STM32 cube ID. Same thing we can able to do here also. We can just we need to give the parameters and we need to click on generate data logger. We need to flash that file. And the data manipulation, let's take we already collected the data set, right? Of course we use it to collect the data sets. So I want to modify some amount of lines or in this specific line, or let's take some, I want to extract some lines, I want to remove some lines, or I want to add some lines. At that point of time, this will help us. We just need to add our file here, we just need to import our file here. After importing, we need to extract it, or whatever the things we have in our mind, we can able to do it in this data manipulation. If we need to check for the sampling for this, yes, we can able to check for our data, and also for the feature importance also we can able to do. Now without any delay, I just want to show to you how this Nano AI Studio is working. I already created one project. Right now I will just show to you that project only. Let's take this overload current sensor. Okay. So here I have selected the anomaly detection one. If you, I will just give just for 1 minute. Okay. Here I just created the project anomaly detection. What the things you want to add here is you want to give your project name. You want to select your board under this, under the HTML32 development boards, and whatever the board you opted for, and you just want to select the sensor. After selecting the sensor, you can directly move on to the signal collection part. So the same thing I have done it, I will just show to you. Here is the overload current sensor. Let's take, I given my project name, I selected the target, and I selected my sensor, which is the current sensor. Okay. I will just click on the save, means whatever the things I have done there. Now, here it is showing me a regular signal and the abnormal signal. Let's take in the regular signal, let's consider again with respect to the industry scenario that the motor, there are big motors. Let's take we are from the electrical, so power plants. In the power plants, how the things will be there, uh, generator will be there, right? So it is generator means it is for the electrical people. We use it to take care with respect from the generator to the complete head that lines, right? Transmission lines. So in the generator, um, there every day continuously it is running. Even though if we need to stop that particular power plant also, it will take around days, right? So manually going and inspecting the particular problem, what exactly is happening inside that big missions, it is it is not possible, right? So at that point of time, what the people will do in the second scenario, there is one big control room. In the big control room, the people will sit and the people will monitor how things are going on. If anything is going abnormal, then they directly, with the one click in their laptop, they will stop it then and there, right? At the after the supervision. So here, why I am telling that scenario is here we are just considering whatever the things I have shown to you, the motor I have shown to you, a small DC motor, we can assume like that, or we can assume the DC mission, whatever we have in our electrical missions lab, which has the 19 amps, the rating current. We already done it in the electrical department. The same thing with this ACS 723 sensor. We already set up the labs and everything in the electrical departments as well. Okay, so this is one of the project. Let's take in the regular signal. How I will do is, okay, there are three ways are there. One is the import signal from the file, one is log signal from the serial USB, and create data logger. Now, I already connected my sensor and everything in the live. I will just click on the log signal from the serial USB. I will check with the COM port, and I am showing to you how this thing will come. Okay. Now I will just run this. Okay. I'm running this. Yeah. If you're seeing, see here, I'm just running this, and values are means this is the current what the current is flowing inside the DC motor. We know the rating, right? So it is around it is taking as of now for uh, 0.3 amps, 0.39 amps, or 300 milliamps, 400 milliamps, like that. Okay, so this is the regular thing. I just collected regular signal. Under the regular signal, I haven't given any load to my particular DC motor. I haven't given any load. We know that if the load is increasing, obviously the current rating will also increase, right? So for this normal signal collection, I haven't given any load here. But whenever we are giving for the abnormal, we need to collect the data set completely with the load. Let's take now I have collected without load, right? In the regular signal, we need to collect without load. In the abnormal signal, we need to collect with load. That's it. After completion of the collection of the signals, the data sets, we will move ahead to the benchmark. Okay. So generally, what happens in this benchmark is like NanoAJ Studio in its server, it has so many pre-trained machine learning models are available. So whatever the data sets we already collected, so it will take the data sets. This NanoAJ Studio will work with the online, so it should have the internet. Whatever the data sets we are sending to that server, so it will check with respect to the data sets. It will give the best out of it. Yes, I have the best out of it. So this is my best library results. It will takes in the form of similarity scores. Okay. So uh, it is giving me 20 iteration cycles. And one more thing is like this anomaly detection is a dynamic model, means it will expect the training again from the user end. Means you will see how it will expect the training. Means with the help of that training only, it will try to predict the outcome. Now, how many iterations it is expecting as a learning process? 20 number of lines. So it is expecting from me that you want to give 20 number of lines for the proper outcome to detective overload, like that. So I will go to the validation section. So this validation is very useful for us, because uh, generally, if anywhere you see, if you want to build an ML model, you will directly and you will complete the ML model building. At the final stage, what you will do is you will at the time of deployment stage, at the time of final deployment stage, only you will get to know whether your ML model is working or not in most of the scenarios. But what is the useful for this NanoJ Studio is whatever the data set we collected, it is giving us an opportunity to check whether you satisfied with the predicted outcome. I will just show to you in the serial emulator here. Yes, it is asking me to give the 20 minimum 20 number of lines for the training. I will give completely the normal data only. Okay, I'm just giving, if you check the uh, rating here, current rating 0.3. So it is giving us an opportunity. Directly don't go for the deployment. You can check whether your model is working here properly or not. Then you can go for the final deployment stage. Okay, I have collected 20 and I will go to the detection now. I will just click on the start. Yes, it is showing me completely 100% similarity score. Right. Now, what I want to tell is whenever you are giving the training previously, whatever the thing we have done, right? The training part, you want to give completely the normal signal only, means without load, no load condition we need to give. So after completion giving the training, the learning phase, we are moving ahead with the detection. In the detection, what we are seeing here, we are seeing in the form of similarity score 100%. Means it will check the data set whatever you have trained the previously 20 cycles, and now whether it is matching the both data sets or not. If it is matching, yes, the motor is running in normal condition without load, means it is completely in a regular signal, means the similarity score is, in terms of similarity score, we are checking 100. Now if you're seeing, I will just add some mechanical load on my motor. I'll just add some mechanical load. Means some load is being detected here, right? So at that point of time, I'm checking in my screen that, okay, load has been detected with, means the similarity score is decreased, means the load is detected. I now I remove the mechanical load. Now everything is back. Right. I will just give the mechanical load again. You can set any kind of thresholds as well. So many things we can able to do. Yes. If the current values are increasing, I have trained like that only. The load is increasing, current will increase. So I'm considering that higher current as an anomaly here. Okay. I hope this is clear. Now, I will just stop this. Yes, finally, I have checked directly in the NanoJ studio only without going to the deployment stage. Yes, I am satisfied now. My model is properly working. Now I will move ahead with the deployment. I will make use of these libraries. There are a lot many MLs are there, ML models are there, like ZSM, zero score model, MML, and IPCA, principal component analysis. So whatever depends on your requirement. So we just need to move ahead like that. This is one of the way to build an ML model, right? Here, Rohit already told to you. One more is cube.ai. So you can able to build your ML model from the scratch. Let's take your presenting any you want to publish any research papers at that point of time, that tool also will you can able to useful. So you can able to build an ML model from the scratch. You can get the graphs with the cube.ai tool. And this NanoJ Studio, it will only expect the training from the user end with the help of the data sets. With the help of that training properly, we will get some libraries and we'll give that libraries at the deployment. I will go to the deployment. I will click on the deploy library. We'll go to the deploy. So I will just save this library uh, into my desktop. Okay. So this is the one. This is the one. I will just extract it. Okay. So in this, if you're seeing, we have few folders in that unzipped folder. We have again some folders and some files. So we can make use of this nanoJ.h header file and the main library file. So for that reason, again, now I'm moving ahead with STM32Cube IDE where I want to program it. Finally, the deployment one. I already created a project. So this is the deployment project. Here, what I have done here, I included this Nano Edge AI.h, what I got from Nano Edge Studio zip file, and libneai library Nano Edge AI.a, the main library for us, whatever the training, whatever the things, what we have given completely, the main library. So I am attaching under my project directory, right? So later, I already given the paths as well. After giving everything, here all the driver files also I have added. I have written the code. So how I have written the code? I have included everything here, ACS723, nanoaj.h, and yes, means I already got some idea from the NanoJ Studio that it will expect the training again from the user, and the same thing I want to give here as well. Yes, done. And with respect to the similarity scores, we are checking the output. If it is 100% similar, then it is completely without load, no load condition. If it is decreasing its score, then load is detected. Motor, DC motor. Okay. So the same thing here also. I'll just go to here. I'm using some train function. In this train function, I'm learning the cycles. And here at the inference phase, I'm checking with respect to the detection and learning. If you're seeing here, training, I'm using NanoJ or NanoJ Studio, anomaly detection, learn. And in the inference, I'm using detect. Okay. So this is also, I got some idea from this nanoj.h only. What I got from NanoJ Studio. Okay. Here only we are seeing one statement that the percentage of similarity is 0 to 100. Right. 100 means completely similar. 0 means completely dissimilar. Okay. Yes. Now everything is done. I will flash my final deployment code. In this only I have attached in my main library what I got and header files what I got, and I have written the logic, and I will check whether the model is predicting or not. Okay, I have flashed it. Uh, I will just open one console. There are a lot many ways are there. You can make use of the inbuilt this cube console option. So I prefer using the putty to check my output. Yes, my HTM board connected with the device manager. I have checked this. It is connected with COM12 for me. So I will the baud rate 115200 and I will click on enter. Okay, now I will press the reset button on my microcontroller board. It will restart the training. Okay, I have given the 20 number of training cycles. So we'll wait for the 20 cycles. Okay, so now what we saw in our NanoEdge Studio in the validation section, here also we are seeing the same thing. Similarity score is 100%. Means the motor is running without load, right? Now, if I just give some mechanical load, just observe the similarity score. We can keep some threshold, some overload got detected. Okay, if the similarity score is decreasing below 89 or below 80%, so we can integrate some IoT concepts as well for this. So now I'll just make show to you. Okay, so this is the mechanical load I am applying. I will just remove my hand. You people are clearly seeing that the similarity score is back to 100, right? Okay, so by this we can able to easily predict whether the overload condition our motor is running with the load condition or without load condition. We can able to implement this ACS723 sensor. It has an uh, higher voltage rating as well. We can able to connect it for even though for our electrical machines lab, and we can check. We can directly connect the 230 volts to the positive pin because it will works with the Hall effect. It won't damage the circuit internally. So that is the reason. But as of now, for the demo purpose, means for this FTP, so we just want to show to you. We want to give the knowledge to you people. So that is the reason we have just tried with this small DC motor. It will works with higher end motors as well. Yeah. So this is the final deployment. So that's it from my end. I just want to take some questions, Mr. Rohit.
Yeah, Chiranjeev, I'm there. Yes, Chirag sir. So that was all from our end. If there are any questions, we are open to that.
Thank you.
Thank you. Thank you very much. Any question,
Uh,
participants?
I hope we have one question in chat, Rohit.
Any question?
Yeah,
Participant,
there is a
please.
question on chat box, sir. How do you compare STM32 with DSP processor TMS28335 for power electronic application?
Okay, so that I will take. Usually, there is there is difference between these two processors. The TMS 28335 is from TI, and again, this is normal. These are normally known as DSCs, digital signal controllers. So, the the processor, the overall architecture has been designed in a way to support multiple PWMs and deliver more power to motor control applications. Rather, STM32, the one which we showed in the demo, or traditionally the microcontrollers that I have been talking about. So STM32, they are more general application-oriented microcontrollers. It might not be very much suitable for very specific applications, such as motor control only. Okay. Uh, uh, so if I would have to say, 60% both are same. 40% in case of TMS 28335, it's more oriented towards motor control applications, like availability of number of PWM channels, the way you can control the PWM channels and all, right? So that is how these two are different, but both are, both are microcontrollers in ARM Cortex domain only. Yes.
Yeah, Dhruang Gaikwad has a question. Please, Mitesh, can you make him unmute him? Dhruang
यस
Gaikwad.
सर अनम्यूट अनम्यूट किया है सर
Okay,
माइक
okay.
माइक अलाउ
Yeah,
किया है
please, Dhruang, Mr. Dhruang Gaikwad, please ask the question.
Cost, Rajiv sir का कुछ
Hello.
question है? Yes, sir. Audible, sir.
Hello.
Please go.
Yes, yes, please.
Please go ahead, sir.
So my question is, can someone is not good enough in programming, and but he has a logic. Let's take an example of APFC panels, and he wants to maintain the power factor. Okay, so can it simply possible with the help of this what are this nano edge AI or this STM32, what the software you shows already? So simple that if analysis logic or whatever the condition I have given, or in the term of the Excel sheet, okay, what is the whatever is the data, my load variation is fixed. So can we simply implement it with or can this software make the ready-made programming?
Yes, sir. I mean, with NanoGI Studio, no, even if you don't have machine learning expertise or you're not familiar with the programming, you can go ahead. Only thing is you need to have data set with you. It can be in the form of CSV, Excel, whatever. Okay. So if you have data set with you, if I understand correctly your question, so if you have data set with you, you can give those data set as input to the NanoGI Studio, and train your sorry, not train, first maybe evaluate your model, benchmark, do the benchmark process, then possibly do it on the emulator part also. So you can use without hardware also, you can use NanoGI Studio. Only NanoGI Studio you just need to install, and you can use with offline data also. Yes, sir.
But sir, in the later section, you shown that some of the programming I can only see the
Ji
if
sir,
else
ji.
and while loop all that. I
Correct,
didn't see
correct.
anywhere the logic. So
वो
the
deployment का
data
था
sheet
sir.
is there. हाँ वो data
Correct.
sheet तो था sir, but
जी.
the motivation should be there that one simple logic can be implemented with the AI or ML. So whatever I show that is totally the programming language, but
जी
is
sir.
similarly available in the MATLAB code also. So
Correct.
without knowing that no one can directly configure that anyone means any problem can be solved without that programming.
सो यहाँ पे जो हमने दिखाया है सर, बेसिकली रियल टाइम सेंसर से जो आप डेटा ले रहे हो, राइट? सो वेन एवर यू टेक डेटा फ्रॉम द रियल टाइम सेंस, मे बी लेट्स से यू हैव योर ओन डेटा एक्विजिशन सिस्टम एंड यू वांट टू डेवलप ए मॉडल for that system, okay, and deploy it. Then all your workload on the machine learning part can be saved. Yeah, you can do it on MATLAB also similarly, but this tool has been designed specifically for microcontroller based systems. So the optimization that you will get with this NanoEdge AI Studio will be very different from what you can get from MATLAB. And NanoEdge AI Studio का जो model it gives you, right? This is production ready models, so you don't have to worry about the performance or something. It will work in every condition. Okay. तो नॉर्मली या कोडिंग विल बी देयर. अगर आपको खुद के ही डेटा एक्विजिशन सिस्टम से डेटा लेके, जैसे सेंसर से डेटा लेके फिर उस पर डिप्लॉय करना है, तो ऑब्वियसली लिटिल बिट ऑफ कोड विल बी देयर, बट मशीन लर्निंग पार्ट पे आपको कोई कोडिंग नहीं करना है.
Yeah, for example, sir, I want to ask that suppose transformer condition monitoring है already. ठीक है,
जी.
जैसे आपने मोटर का बनाया, अगर वैसे ही
Correct,
जैसे
correct.
मोटर का कंडीशन मॉनिटरिंग आपने जो थियरी पोर्शन में स्लाइड में दिखाया था,
जी
सो
जी.
अगर वो डेमोस्ट्रेट करते तो ज्यादा मतलब प्रैक्टिकली होता, फिजिबल होता और कुछ नहीं.
Actually, correct. The
Rohan sir,
reason
we have
because
183 participants, right? Everyone has a
Yeah,
different
yeah.
problem, right? We can't
no,
give
Yeah,
sir,
yeah. No,
sir,
that's a
question
suggestion,
is
sir,
very
from my
right.
side of view.
थैंक यू सर फॉर द सजेशन. द रीजन कि यहाँ पे जब डेमो हम सेट करते हैं ना, बहुत हमारा लिमिटेड हो जाता है चीज़. मतलब यूजुअली
it
लाइक
has
वी
to
हैव
be.
टू मेक इट ऑन स्मॉलर थिंग्स, क्योंकि हम इसको टेबल टॉप पे कर रहे हैं, राइट? दैट इज द रीजन. तो कॉन्सेप्ट हम दिखा देते हैं, ऐसा कर सकते हैं, बट सेम चीज़ को यूज़ करके लोगों ने रियल फील्ड में भी ही किया है. और अगर आप एसटी के वेबसाइट पे जाते हो तो बहुत सारा ऐसा डेमो है जो रियल फील्ड का
Available,
आपको
right?
मतलब एक ग्लिम्स दे सकता है उस. ठीक है.
Yeah, one question, Rohit, from my side,
जी
if you
चिराग
can
सर.
help me. Yeah, actually, this nano edge AI, do
जी
we
सर.
directly give signal data? Or we have to give the features extracted?
I mean, NanoEdge Studio ka data sheet, if we go through that, it asks you to
Mhm.
go give raw data also. I mean, most
Okay.
of the times raw data will work, but specific जैसे अभी आपका for a certain audio applications रहता है ना, जैसे
Yeah,
आप
then
अगर
obviously. Okay.
MFCC वगैरह करना रहता है, तब definitely at that moment we have to extract the features and give it.
Features, and then we
और
have to
या फिर
provide features,
correct,
right?
yes yes yes.
Okay.
But ऐसे सेंसर बेस्ड जैसे इलेक्ट्रिकल सिग्नल्स में तो नॉर्मल भी दे सकते हैं. लार्जली बहुत सारे एप्लीकेशन में नॉर्मल ही लिया है हमने.
Okay.
Yeah.
Okay. Thank you. Thank you very much.
Participants, if you have any question, you may ask question.
So
No
cost
question?
STM32
question.
बोर्ड का कॉस्ट कुछ 3,000-4,000 रुपए में आ जाता है. ऑनलाइन आप देख सकते हैं उसका.
Yeah.
So it's cost around 3-4K. Yeah. STM32 boards.
Yes. Yes. Okay. So I think there is no more question. We can conclude this session. Thank you very much.
Sir, one
Yes.
question.
Okay.
Can
Yeah.
Nano Edge AI Studio be effectively used for real-time detection and short-term forecasting in renewable integrated microgrids?
Okay, can be used effectively used for real-time detection. So real-time detection, what kind of detection?
Renewable integrated microgrids. Forecasting
Renewable,
But exactly,
short-term
please
forecast.
elaborate exactly what exactly you want to detect. Anomaly
Short-term
or what?
forecasting in
Sabirali
renewable.
Champa.
Yes,
So
sir. Can you
usually,
elaborate?
yes, sir.
Sabir Ali.
And short-term forecasting in renewable, short-term forecasting in renewable.
I think, sir,
integrated.
he's referring to wind forecasting, etc.
But what does
Yeah.
I mean?
Wind
Ji, sir.
speed, or let's say something like that, wind power.
See, we
something like
have like Chiranjeevi showed demonstration on anomaly detection, I guess, right, Chiranjeevi?
Yes,
Yeah.
Rohit.
Yeah. So there are algorithms which are also used for regression applications. I mean, basically for predicting things. Okay, so if you give a set of parameters as inputs, it can give you output based on the predictions also. So NanoEdge AI Studio algorithms, right, or the models generated as outputs are highly flexible. I mean, we have seen applications where it has been used across different use cases. So if I just generalize the answer. So obviously it can be used for real-time detection, because at the end of the day, it is deployed on the hardware itself. As soon as your sensor data comes, the model gets trained. We already have a trained model, and it does the detection process. It can be anomaly detection, or it can be maybe fault detection, different types of things we have already been implemented. But yes, again, maybe if you want to customize it for some specific segments also, you can do it. You can even combine different algorithms here. Like you can combine anomaly detection with classification. So multiple algorithms को भी आप combine कर सकते हो कुछ specific use cases के लिए. Otherwise, सर अगर थोड़ा और elaborate करके आप इस email ID पे भेज देते हैं, I will just share my email ID. तो maybe possibly we can give you exact response on this. You can please share on this. rohit.p@digitotech.com. So chat box पे
Okay.
मैंने दे दिया है जी.
Okay.
Sir, please one group photo, sir. Please turn on your camera, sir. Yes, Chiranjeevi. Hello. Hello.
Yes, Ravi sir, you are not visible.
I am not visible.
No.
Okay. One second. Now? Hello?
No.
No.
Yeah, anyways, we will take a
Okay.
photograph. Okay.
Okay.
Okay, sir. So, thank you very much, Mr. Rohit Prajapati and Mr. Chiranjeevi. It was a very interesting session. It's well supported with the demonstration. I believe participants have gained lots of information from this. Thank you very much.
Thank you, sir. Thank you for the opportunity. We look forward to attend, participate in more such sessions. Please feel free to reach out. Okay,
Yes,
whenever
yes.
you are
Sure.
organizing such things, and it's always a pleasure to interact with faculties and maybe get all these beautiful questions from their end. And it's learning for us at the end of the day. Thank you so much. It was pleasure delivering the session. Thank you so much.
Thank you, sir.
Thank you, sir.